Part 1. Thermochemistry.
Thermochemistry measures the heat changes associated with chemical reactions. In other words, thermochemistry deals with how much energy moves around as a result of a reaction. We measure energy in joules, which is an SI unit of measurement.
Section A. Enthalpy. Enthalpy.
Before we dive into enthalpy, let's straighten out a few of the associated terms. System refers to all the substances taking part in a reaction, including the reaction vessel. Surroundings refers to the rest of the universe.
Here's an example. Let's say we have some vinegar in a beaker and we add a couple of grams of baking soda. The baking soda will react with the vinegar in the beaker, creating a stinky, bubbly mess. The beaker is part of the system because it is the reaction vessel. Everything outside the beaker is considered the surroundings. Chemists widely use Greek letters to stand for words in mathematical equations. The Greek letter delta, which to you non-Greeks looks like a triangle, it just means the change in something. As you study enthalpy, you'll see a lot of equations that have deltas in them. Just read the delta as the change in. When you see delta H in enthalpy equations, you can just read it as the change in heat.
Now, here's the scoop on enthalpy. Enthalpy is just a fancy word for the amount of heat in a system at constant pressure, the system being whatever part of the universe you've decided to study. Enthalpy considers the heat that flows out and the heat that flows into the system. In other words, the change in heat that happens as a result of a reaction. And as the guy in the toga mentioned, the change in heat, the difference between the amount of heat you started out with and the amount of heat you ended up with, is represented in the equations by the Greek letter delta. The letter H stands for heat, so delta H stands for change in heat.
When you measure the enthalpy change that occurs during a reaction, delta H is equal to the enthalpy of the products, or the stuff you end up with at the end of the reaction, minus the enthalpy of the reactants, or the stuff you started with at the beginning of the reaction. This equation represents the change in the enthalpy.
There are two types of reactions which involve the exchange of heat: endothermic reactions and exothermic reactions. In an endothermic reaction, heat flows into the reaction. When heat flows into a system, the change in heat, or delta H, for the reaction will be a positive number. The endo in endothermic kind of sounds like into. Endo, into. See? It makes sense that in an endothermic reaction, the change in the amount of heat is a positive number because there is a positive heat flow into the system.
When heat flows out of a system, on the other hand, it is an exothermic reaction. That's real easy to remember because exo sounds like exit. In an exothermic reaction, heat is exiting the system. When you calculate how much heat exits the system from an exothermic reaction, the number you get for delta H will be negative. That makes sense too. When heat exits the system, you have a negative heat flow. The heat is going out.
During an exothermic reaction, the heat flows from the reaction system to the surroundings. Bobo the Clown's propane stove is the reaction system, and Bobo is part of the surroundings. The propane stove is creating an exothermic reaction, and the heat from the reaction is flowing into the surrounding area, and into Bobo's weenies. In an exothermic reaction, delta H is negative.
During an endothermic reaction, there is a flow of heat from outside going into the reaction system. For example, when little Joey tied his father's shoelaces together, little Joey's dad suffered a nasty bump on his head. Dad is taking advantage of the endothermic reaction going on in the commercial ice pack. The chemical reaction in the commercial ice pack draws the heat from the warmer body, Dad's bruised and lumpy head, to the cold ice pack. So the ice pack is the reaction system, and the heat from the surroundings, in this case, Dad's head, is flowing into the reaction system. In an endothermic reaction, Delta H is positive.
Standard enthalpy is the heat exchange during a reaction when the reactants and the products are in their standard states. A substance is in its standard state under these conditions. These are standard for all substances. The substance must be at 25 degrees Celsius, 1 atmosphere pressure, and in its most stable form. Pressure refers to the pressure exerted on the substance by the air around it, and an atmosphere, which is abbreviated ATM, is simply a unit used to measure pressure.
The standard enthalpy of formation, or delta H of formation, is the enthalpy change, or heat change, during a reaction that forms a compound from elements that are in their standard states at 25 degrees Celsius and 1 atmosphere pressure. In other words, elements in their standard states form a compound that's in its standard state, and the heat exchange that happens during the reaction is called the standard enthalpy of formation.
Now here comes some good news. You don't have to calculate enthalpies of formation. Some nice chemists did that for you. You can just look them up in a table in your chemistry textbook. Also, the standard enthalpy of formation for all elements is 0. You can plan on it. That's only true for elements like helium, oxygen, or copper. Compounds are different. You need to look up the enthalpy of formation for any compounds. So you don't need to calculate standard enthalpy of formation for elements.
At Atomic Mass University, we have an academic program renowned throughout the molecular universe. We offer courses in everything for the undergraduate particle, including stoichiometry, comparative enthalpy, orbital studies, and business administration. Plus, AMU's academic program is accredited by the law of conservation of mass, Avogadro's constant, and the first law of thermodynamics.
Okay, here's another rule for you to remember. It's called Hess's law, and it's pretty easy. According to Hess's law, the total enthalpy change for a reaction equals the sum of the enthalpy changes of the intermediate steps. In other words, if your total reaction consists of 3 little reactions, you add up the enthalpy changes of the 3 little reactions and get the total enthalpy change for the reaction. Just remember it, because you'll need to know it for a problem.
Using Hess's law and what we know about the standard enthalpy of formation, we can calculate the enthalpy change for a reaction with this equation. The enthalpy change of the reaction equals the sum of the standard enthalpy of formation for each of the products, or the stuff you end up with, minus the sum of the standard enthalpy of formation for each of the reactants, or the stuff you started with. Put on your toga and we'll show you how to use this Greek-looking thing.
Here's the reaction between sulfur dioxide, SO2, and oxygen to form sulfur trioxide, SO3. To find the standard enthalpy change that goes along with this reaction, first take the standard enthalpy of formation for SO3, the product, and multiply it by 2, since the 2 in front of the SO3 in the product indicates that we have 2 moles of it. This is the enthalpy of the product, the sulfur trioxide we end up with. Then subtract the sum of the enthalpies of formation of the reactants, the starting stuff. That's 2 times the standard enthalpy of formation of SO2 plus the standard enthalpy of formation of O2. Remember, the numerical values for the standard enthalpy of formation for each chemical can be found in tables in any general chemistry textbook. So don't stress about it, just look them up and plug them in. The standard enthalpy of formation for our product, sulfur trioxide, is negative 395.2 kilojoules per mole. For sulfur dioxide, it's negative 296.9 kilojoules per mole. And for oxygen, the standard enthalpy of formation is 0, because the standard enthalpy of formation of any element is always 0.
So here we substitute the values into our equation. We have 2 times negative 395.2 minus 2 times negative 296.9 plus 0. That equals negative 790.4 minus negative 593.8. Subtracting negative numbers is just like adding, so we get that the total change in enthalpy for this reaction is negative 196.6 kilojoules. Since the change in energy is negative, that means that the heat is exiting the reaction.
Heat is flowing out of the reaction. What kind of reaction is it? Exothermic, sir!
If it was positive, it would be an endothermic reaction.
So, enthalpy is the heat exchange that happens during a reaction. When heat exits the reaction is called exothermic. When heat goes into a reaction from the surroundings, it's called an endothermic reaction. The standard enthalpy of formation is the enthalpy change during a reaction that forms a compound from elements in their standard states at 25 degrees Celsius and 1 atmosphere pressure. Hess's law tells us that the total enthalpy change for a reaction is the sum of the enthalpy changes of the little reactions that make up the total reaction.
Section B, calorimetry.
Calorimetry measures the heat absorbed or created in chemical reactions.
Rock and roll, dudes!
The heat absorbed or created is determined by heat capacity and by molar heat capacity. Heat capacity is the amount of heat you need to raise the temperature of an object or substance by 1 Kelvin. Molar heat capacity is the amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin. The heat capacity of 1 gram of a substance, which is the heat required to raise the temperature by 1 Kelvin, is called specific heat. Specific heat is another thing you can just look up in your chemistry textbook. Don't you just love that?
Let's hear those again.
Heat capacity is the amount of heat required to raise the temperature of an object or substance by 1 Kelvin. Molar heat capacity is the amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin. Specific heat is the heat required to raise the temperature of 1 gram of a substance by 1 Kelvin. You can look up specific heat in a chemistry text.
The specific heat of lead is 0.129 joules over grams times Kelvin. So that's the amount of heat required to raise 1 gram of lead by 1 Kelvin. You can find this number on a specific heat chart in your book. So how many joules of heat are required to raise the temperature of 291 grams of lead from 21.9 degrees Celsius to 40.8 degrees Celsius? We'll use this new formula to find out. The quantity of heat needed equals the change in temperature times mass times specific heat. Remember, as with any calculation, watch your units. The units of specific heat include Kelvin in the temperature, not Celsius. This formula lets you determine how much heat you need to add to a substance to heat it up a specific number of degrees. This is an easy problem because we have all this information already. Some of it's in the question, and we looked up the specific heat of lead. It's 0.129 joules over grams times Kelvin, so we just need to plug in the numbers. If you noticed in the problem, the temperature is in degrees Celsius, but specific heat uses kelvins. And this isn't a problem since we're looking for a temperature change. We can use the fact that a change of 1 degree Celsius equals a change of 1 Kelvin. So, our change in degrees Celsius is equal to the change in Kelvin, and we don't have to worry about it. Our change in temperature is 40.8 degrees minus 21.9 degrees, which equals 18.9 degrees. So plug that in. The mass we are dealing with is 291 grams, so plug it in. And the specific heat of lead is 0.129 joules over grams times Kelvin, which we found on the chart. So that goes in there too. So we have Q equals 18.9 Kelvin times 291 grams times 0.129 joules over the quantity grams times Kelvin. The amount of heat we need to raise this 291 grams of lead by 18.9 Kelvin is 709 joules.
So, calorimetry measures the amount of heat absorbed or created in reactions. Heat capacity is the amount of heat required to raise the temperature of an object or substance by 1 Kelvin. Molar heat capacity is the amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin. And specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 Kelvin. You can look up the specific heat of substances in your chemistry textbook.
Part 2. Atomic structure.
Most of the stuff you've learned so far in chemistry has to do with formulas, calculations, and terms. Quantum mechanics is a little different. It's not anything you'll have to calculate or measure. It's more of a concept, a theory explained with numbers, letters, and pictures. The quantum mechanical theory helps us understand where the electrons are in atoms and molecules. Now, it's important for us to know about where the electrons are because electronic properties, like the properties that determine the shapes of the molecules, depend on where the electrons are. So pay close attention to this stuff and don't get frustrated.
Section A, Quantum Mechanics.
Quantum mechanics is a theory of the behavior of electrons in atoms and molecules. Of course, electrons are unbelievably tiny, so figuring out where they are and what they're doing at any particular moment is really hard. One problem that scientists have run across is deciding whether the electron should be considered a particle that's localized in space or a wave that's spread out in space. Scientists call this dilemma wave-particle duality. A few, like Erwin Schrödinger, dedicated their lives to studying this perplexing problem.
Schrödinger decided that the best description of electrons' behavior combines the particle and the wave ideas. And most scientists agree. He used some big ugly math as a basis to construct pictures of where the electrons might be in atoms and molecules. These theoretical representations, called orbitals, show you where the electron is 90% of the time. An electron's orbital describes three things about the electron. Number one, its average distance from the nucleus of the atom. Number two, what shape its possible path forms. This shape is called the distribution. And three, how the distribution is oriented in space. In other words, where it is in relation to the atom's nucleus and the other orbitals.
Remember those three things. An electron's orbital describes 1. Its average distance from the nucleus of the atom. 2. What shape its possible path forms. This shape is called the distribution. And 3. How that distribution is oriented in space. In other words, where it is in relation to the atom's nucleus and the other orbitals.
These three characteristics of an electron's orbital are described by three numbers, called quantum numbers.
Quantum numbers. Quantum numbers.
Now these quantum numbers are a little weird, and they all relate to each other, so bear with us.
The first, or principal quantum number, is represented by a lowercase n, and it describes how far, on average, the electron is from the nucleus of the atom. The second quantum number is represented by a lowercase l, and it's called the azimuthal quantum number. It describes the shape formed by the electron distribution, or the shape of the possible path the electron can take. Finally, m sub l, the magnetic quantum numbers, describe where the orbital is in relation to the nucleus and the other orbitals. We'll now tell you more about each of these quantum numbers.
The principal quantum number, represented by a lowercase n, indicates how far an electron is, on average, from the nucleus. N can have whole number values of 1 or greater. So you'll see values like n equals 1 or n equals 2 or 3 and so on. As the value of n increases, the orbital gets bigger and the electron can range farther from the nucleus.
Think about the Earth orbiting the Sun. The Sun is like the nucleus. The distance between the revolving Earth and the Sun is like the n quantum number. N tells you how far the electron is, on average, from the nucleus.
The azimuthal quantum number, represented with a lowercase l, defines the shape of the orbital.
Straight from the temple of Azimuthal.
Schrödinger's mathematical distribution indicates an area around the nucleus in which the electron is likely to be. That area, also called the distribution, forms a shape like a sphere shape or a dumbbell shape. We'll get to the specific shapes of the orbitals in a minute. For now, just remember that the azimuthal, or L, quantum number indicates the shape of the orbital.
The L quantum number is related to the n quantum number because L must be a value between 0 and n minus 1. So for instance, if n equals 2, then L must be 0 or 1. If n equals 3, then L can be 0, 1, or 2. And if n is 1, then L must be 0. Chemists use a letter to stand for the L quantum number. The designated letters are S, P, D, and F. So, if L equals 0, we use the letter S to represent that number. If L equals 1, we use the letter P. If L equals 2, we use the letter D, and if L equals 3, we use the letter F. These are standard. Substituting letters for the values of L makes it easy to express the n and L quantum numbers together. You can find this quantum number letter scheme on your insert card.
So for instance, if n equals 1 and L equals 0, you can refer to the orbital as a 1s orbital. If n equals 2 and L equals 1, you can call it a 2p orbital. For a 2p orbital, 2, the n quantum number, tells us how far the electron is on average from the nucleus, and p, the letter representing the L quantum number, tells us the shape of the orbital.
Say this figure skater is an electron going around the nucleus. The shape formed by her path is a lot like the L, or azimuthal quantum number, which tells you the shape of the area in which the electron is likely to be.
The magnetic quantum number, called m sub L, describes the orientation of the orbital in space. In other words, it tells you where the orbital lies in relation to the nucleus and the other orbitals.
The value of m sub L is related to the value of the L quantum number, because m sub L consists of the integers between negative L and L. So for instance, if an orbital's L quantum number is 2, m sub L is negative 2, negative 1, 0, 1, and 2. If L is 3, then m sub L is negative 3, negative 2, negative 1, 0, 1, 2, and 3. So whatever the L is, then the m sub L can have values from positive L to negative L.
I quantum number. Shape of the orbital.
Pretend Dick's dumbbell is the orbital of an electron, and Dick's hand is the nucleus. The n quantum number will tell you the distance between Dick's hand and the ends of the dumbbell. That's how far the electron is from the nucleus most of the time. The dumbbell-shaped path is determined by the L, or azimuthal quantum number. The angle of Dick's dumbbell is like the m sub L, or magnetic quantum number. The magnetic quantum number describes the orientation of the electron's path in space.
A group of orbitals with the same principal, or n quantum number, make up what's called an electron shell. Remember, the n quantum number tells you how far an electron is, on average, from the nucleus. So a group of electrons that are cruising around at the same distance from the nucleus make up an electron shell. All the electron orbitals with a principal, or n quantum number of 1, are in the first shell. All the orbitals with n equals 2 form the second shell. All the ones with n equals 3 form the third shell, and so on, and so on, and so on, and so on.
Now let's get into the details of this quantum number thing.
Orbitals that have the same n and L values form what's called a subshell. You might have a couple of orbitals that have n equal to 2 as the principal quantum number, and L equal to 1 as the azimuthal quantum number. These orbitals will have electrons that congregate at the same distance from the nucleus, and the areas where the electrons are likely to be are the same shape. These orbitals form a subshell.
So, for instance, if there is one orbital with the quantum numbers n equal to 1 and L equal to 0, we say this orbital makes up the 1s subshell. Remember, the letter S in 1s stands for the L value, which in this case is 0. Here's another example. All orbitals with the quantum numbers n equal to 2 and L equal to 1 we call the 2p orbitals, and we say they are in the 2p subshell.